So we know that derivatives represent the rate of change, the change in y as x changes by 1 unit. So we can use that in a lot of applications, and that's what this section is about, to show us some examples. So the difference quotient gives the average rate of change of y with respect to x over an interval from a to b. Again, it tells us how y changes as x changes by 1 unit. And if we do the limit of that, we would then have the instantaneous rate of change. So the derivative gives us the instantaneous rate of change at any particular x value. And to help you interpret it, this is always going to be the units on y over the units on x. So we have an example here from physics with a position function. We know that if we take the derivative of position, we get velocity. We take the derivative of velocity, we get acceleration. So we've got a fairly long example with many parts here we're going to look at. So suppose that the position of some object follows this function s of t is 2t cubed minus 42t plus 12, where t is in seconds and s is measured in meters for our units. Now keep in mind here, position, velocity, and acceleration can be negative. Position's negative if you're moving in the opposite direction from the reference point. Velocity would be negative if you're moving backwards relative to the reference point, and acceleration if you're slowing down. So find the velocity at time t, and then what is the velocity after 4 seconds? Well, we can use the first derivative to do that. To find v of t, the velocity, just take s prime of t, apply the power rule. So 3 times 2 gives me 6t squared, subtract 1 from the power, minus 42, the derivative of the linear term is the slope, minus 42, plus 0. So we get 6t squared minus 42. And then we can plug 4 into that and evaluate, and you get 54 meters per second would be the unit. Again, the units on s, the output, over the units on t, meters per second. So that's our speed, or velocity, in the positive direction. When is the object at rest? When is the object moving forward? Well, the object would be at rest when the velocity is 0. Since the velocity is how fast it's moving, if it's at rest, the velocity would be 0. So we just set our velocity from the previous part, 6t squared minus 42 equal to 0. Solve that, you wind up with t is the square root of t, or approximately 2.65 seconds. When is the object moving forward? That's whenever the velocity is positive. So we could take a look at the graph. I've popped it up here on the calculator. So it's really the negative part. We won't worry about that, but we have from 0 to infinity here. We got 0 at 2.65 seconds, so the velocity is negative till we get to 2.65 seconds, and then the velocity goes positive. So v of t is positive whenever t is greater than 2.65 seconds. Find the total distance traveled during the first 5 seconds. Okay, we have to be very careful here because some of the time it's moving forward, some it's moving backwards. So here's a graph of the position function. So we have the point 0, 12. The object starts 12 meters in front of the reference point and then moves backwards and is at position 0 after 0.29 seconds approximately. And then the position goes negative to negative 62.08 if we find the min there. And then goes back in the other direction and is back to 0 at 4.43 seconds. And then at 5 seconds has moved forward to 52 meters. So we can add those parts up carefully here. So we would have 12 meters. It moved from 12 to 0. And then it went in the negative direction for 62.08, so it traveled 62.08 meters, and then had to come back to 0, another 62.8 meters, and then went 52 more. Okay, so I add those up. I get the total distance traveled would be 188.16 meters. Find the acceleration at time t and after 4 seconds. That would be the second derivative. So we could take velocity and take the derivative of that. Again, apply the power rule. You're going to get 12t plus 0. Plug in 4, we get 48, and the units there would be meters per second squared, because on top you have the change in velocity, which is meters per second, and our input variable is seconds. So we get meters per second, which is meters per second squared, are the units on acceleration. Then graph the position, velocity, and acceleration functions for t in 0 to 10. When is the object speeding up or slowing down? So I've set a window. You can see what I set there. I played around with it a little bit to where I could get them to fit. So here's the position function, the position, and then the velocity function, and then the acceleration function. The object is speeding up whenever v of t is increasing, when the velocity is increasing, which is when the acceleration is positive, which is actually from 0 to infinity, since our acceleration was 12t.